Okay, so now here's the proof of Lemma2. So it's a biconditional, so we're going to do this, so basically a biconditional goes both ways, so a little bit of logic here. So for some of you who may not have taken logic, so biconditional means that we have to prove it going one way and then prove it going the other way. So we have to show that P implies Q and then Q implies P. Now, there are some things like equivalent statements, and that's why I love some of these proofs, because there are different ways of proving the biconditional. Like, for example, you can prove that P implies Q by direct proof, or you could do like what we did in a previous example, proof by contrapositivity, which means that if we could prove not Q implies not P, these two are actually equivalent statements logically. Okay? So to prove this direction, we could also just prove this, and it's the same thing. Also, if we want to prove the converse, right? The converse is, so if the implication is P implies Q, the converse is Q implies P. But there's another equivalent statement to this, and that's not P implies not Q. And this is what we call the inverse. So we're actually going to prove the converse by showing the inverse. Okay? But anyway, little sidebar. Okay, so let's start with one direction. So let's start with the fact that S is linearly independent. Okay? So we're going to go one direction that way. So let's start with the assumption. Suppose that S is linearly independent. Then what that means is no vector S sub I in that set is a linear combination of the other vectors from S. So that means that there is no linear relationship where the sum of those vectors all have non-zero, or excuse me, where some of those, there's no linear relationship where some of those vectors S sub I have non-zero coefficients. There's just no way, right? And we know that by the definition of being linearly independent. Now, what about the other way? So this is where the inverse is going to come in. We're going to prove this by using the inverse. So let's suppose that S is not linearly independent. So this is easier than trying to show the other direction. So we'll start by saying, okay, well, what if S is not linearly independent? We want that to lead to the fact that if it's not linearly independent, then there won't be a relationship where all the coefficients are zero. In other words, we'll be able to find a non-zero coefficient where we can, in that relationship. Okay, so let's start. So if S is not linearly independent, then that means that some Si is a linear combination of the other vectors in S. In other words, we can write S sub I as this linear combination here. Well, if that's the case, then what we could do is we can get the linear relationship by subtracting S sub I from both sides, and we get what? We get C1 S1 plus all the way to, well, I'll just rewrite this. Well, you know what? Here, I'll just do it easier. So I'll just erase this, and we'll make this 0, and I'll bring this all the way to the end, and we'll go negative, minus, minus S sub I. Now, what's so important about that? Well, look. Now I have a linear relationship that's equal to 0 where I know, at at least one of the coefficients is non-zero. Right here. It's -1. And we're done. So since I've shown if it's not linearly independent, I don't get a linear relationship where all of the coefficients are 0. So I just proved the other direction by using the inverse. And that's it. We're done.